Okay, what we're going to do here is demonstrate why the fundamental theorem of calculus for line integrals is true. This proof very much mimics the proof of the fundamental theorem of calculus part 1 from Calc 1, so this should look very familiar. It's also actually underneath it all is Euler's method actually running along. Now remember, the very first thing we have is we have a plane full of arrows. And now the fundamental theorem of calculus for line integrals says the plane full of arrows must be the gradient of some function. If they're not the gradient of some function, we have no such shortcut. Now what we do have also is a curve that's just sort of snaking along, and there's all these arrows along the way. We do have a starting point P. We do have an ending point Q. Just like in the fundamental theorem of calculus, we're going to chop this up into a lot of little pieces. So I'm breaking this up into a lot of little pieces. Now remember, how small do the pieces need to be? So small that on each piece the graph looks straight, and all of the force vectors that we're not drawing here because they're unenlightening look the same on each little interval. They can change from each interval to each interval, but on each little interval we want to zoom in so much that they actually look the same. Now again, the notation we're going to be using is going to be the same kind of notation they use for the fundamental theorem of calculus. In the fundamental theorem of calculus, you'd break this up into t's, but I want to be able to plug in points. So what I'm going to do is call that first point R naught. So R naught's the same as P, and the next one's going to be R1, the next one's going to be R2, then R3, etc. And we're going to get to the very end. I'm going to call that last point Rn. That means we're going to have n little intervals. That's going to make the second last point Rn minus 1. And so we see that Rn equals Q, by the way, and P equals R naught. Now one more thing, just want to remind us, when we look at this, we've been calling this kind of vector delta R, but here we're going to have to actually write it with its components, but that's not that hard, because this is delta x, this is delta y, and so we can see that delta R is just the vector delta x, delta y, like that. And we're going to use that over and over and over. All right, now what are we going to do? We're just going to calculate the work done along that first little interval. And remember how to do this? We take f, we plug in the first point, and that's going to be R naught, and we dot it with a little r vector there. So that's the work. Now we want to take advantage of the fact that this is a gradient vector, so we're going to write this as the gradient vector it is. This should be fx at R naught, and then here should be fy R naught. Remember, that's what a gradient vector looks like. And we're dotting it with a vector delta r, and we know what that one looks like. It's just delta x, delta y, like that. Now we can write out the dot product. So I'm going to get fx R naught delta x plus fy R naught delta y, like that. And this is an expression that we've seen 20 times this semester. That's an approximation of the change in the function value. That's either df or delta f, however you want to write it. Now normally we would just write it with that much notation, but I actually want more notation. It's the change in the function values between which points? Well, just between R naught and R1. So this is going to be f of R1 minus f of R naught. So that's going to be the work done by these arrows along that first little segment. So I'm just going to write that over here. That's going to be f of R1 minus f of R naught. We now move to the second little interval. We get the same kind of calculation, but that's going to be f of R2 minus f of R1. We move to the third little interval. We get the same kind of calculation. This is going to be f of R3 minus f of R2. And this is going to go on and on and on until I get to the last 2 points. The last 2 points should be something like, what do I have here? I think it's f of R n minus 1 minus f of R n minus 2, and I get to the last little interval, and I'm going to get f of R n minus f of R n minus 1, like that. And we want to add up all those little pieces of work just to see what happens. Well, this is something that you should have seen in both in the original proof of the fundamental theorem of calculus and in Calc 2 when you did series, because this is actually something called a telescoping series. It's called a telescoping series because when you add them all together, all the stuff in the middle disappears. Here's f of r1, here's minus f of r1. Here's f of r2, here's minus f of r2. Here's f of r3, here's f of minus r3. This happens over and over and over. F of rn minus 2 would be right here and cancels with that. F of rn minus 1 is right there, cancels with that. And all that we're left with, right, is the very last term over here. This is f of rn minus f of r naught. Remember, Rn is Q. This is just f of Q minus f of P. And funnily enough, that's our estimate. When we take the limit as delta t goes to 0 or delta r goes to 0, the right-hand side doesn't change. Yes, and so when we take the limit on the left-hand side, we're going to get the integral we're looking for. The work done is equal to this. Now, this step right here, by the way, was crucial. Right? We had to write that vector field as a gradient. That's usually not possible, so this is not a shortcut that works a lot, but when it does work, it's really important, and physics depends on it a lot. Meanwhile, boy, does this look like the fundamental theorem of calculus part 1. Remember, the fundamental theorem of calculus part 1 says that if you can find an antiderivative of something, you can just find the antiderivative, plug in the endpoint, plug in the starting point, and subtract. If you look in the summary, you're going to see the exact same statement here, and that's why the fundamental theorem of calculus for line integrals is true.